So today, we're gonna talk about the energy stored in a capacitor. You know already what's the function of capacitor. Capacitor stores charges as well as electrical energy. Alright, now how to charge a capacitor, if you can still recall. So I have here a capacitor consists of two parallel plates. This is the simplest form of capacitor. And then between them is a dielectric or say vacuum. Okay, so if to charge the capacitor or to charge these two plates, we're going to connect that to a voltage source. Okay, the purpose of voltage source is to do work by transferring the electrons from one plate to the other plate. So this plate is positively charged since it loses electrons, and then those electrons loses by this plate will be gained by this plate. So this plate will be now a negatively charged. So the amount of electrons loses by this plate will be the amount of electrons that gained by this plate. Now, since once the charge is established, you can disconnect. Alright, so we can disconnect these plates to the voltage source. So we charge already the capacitor. Now, so look at what will happen if I'm going to connect this capacitor to this bulb. Okay, what happened? Okay, so it light up the bulb. So where this light energy came from? It is from the electric energy stored in the capacitor. Okay, so again, let us charge and then disconnect, and then the energy stored in the capacitor will be used to convert into light energy or heat energy. Okay, so electrons will, at first, when you charge the capacitor, electrons will flow from this plate to that plate. Okay, so this plate will become positively charged and this plate will become negatively charged. And then when you connect to a device like computer or bulb or any device that uses capacitor, when you connect that, so the flow of electron will be from this plate to that plate. Okay. So there is work done by transferring the electron from one plate to the other plate. And the amount of work done to move an electron or electrons from one plate to the other plate is equivalent to the electrical energy stored in the capacitor. Okay? So the amount of work done by the battery, or work done by the battery to move the electron from one plate to the other plate is the amount of energy stored in the capacitor. Okay. But how to obtain the amount of energy stored in the capacitor? So capacitor not only stores the charge but also stores energy. So when battery is connected to the capacitor, electrons of total charge negative Q are transferred from one plate to the other plate. So that's how you charge a plate of a capacitor. You need to connect that into a voltage source. To transfer the charge, work is done by the battery. And the work done is stored as electrostatic potential energy in the capacitor. So the amount of work done by the battery to move the electrons from one plate to the other plate is equivalent to the electrical or electrostatic potential energy in the capacitor. Suppose these are the two plates of the capacitor. Okay? Now, if we're going to attach these two plates, then you cannot charge these two plates because the electron from this plate will continue to move around the circuit. Okay, when you attach these two, because these two plates are conductor. If we attach this plate to the other plate, then there is flow of electron. Okay, so the charge will not stay on this plate, but rather it will flow. Now, if we're going to let these two plates be in distance d, okay, we're going to separate this two plates by a distance d, right? So there is work done when you separate, okay? And that work done is equivalent to the work done to move the electrons from one plate to the other plate, right? So again, there is work done when you separate these two plates, okay? And the work done in separating these two plates is equivalent to the electrical potential energy stored in the capacitor, okay? So work done, as you can still remember, work done is the force times distance x, or dx, okay? So this is the work done to move charges, okay, from one plate to the other plate. So there is force exerted to separate these two plates, and that is F, right? And we know that F, since work done is equivalent to the charge or the energy stored in the capacitor, then I'll make that as U to emphasize that this is a potential energy stored in the capacitor. So the equivalent work done, the work done is equivalent to the potential energy stored in the capacitor, which is force times the distance x. So we consider a small distance d, so we need to integrate this. Integrate meaning add all distances. So small distance dx, 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 dx. So we're going to add all dx here. That's equivalent to the integral of dx, right? So the sum of all dx here is equivalent to the distance between two plates. So that's from 0 to d. Start 0 here, then d here. So we have the electric potential energy will be force times distance d. Alright. Now the force, the electrostatic force, is equivalent to the charge Q times the electric field. So I will plug in F by with this Q times the electric field. So the potential energy is Q times the electric field times distance. Okay. Now you know that the electric field, okay, let's consider the electric field between these two plates. Okay, there's electric field between the two plates is the charge density, areal charge density over the permittivity of free space. Okay, so if you can still recall the electric field between two plates, one plate is positively charged and one plate is negatively charged, and the areal charge density is the charge per area. So electric field is charge per area times permittivity of free space. So the charge is the electric field times the area of these two plates, area of either of these two plates times the permittivity of free space. Okay, so since there are two charges, one positively charged and one is negatively charged, then we'll get the average charge, or Q average, and that is equal to the electric field times the area times the permittivity of free space over 2. Alright, so we'll plug in the average Q by electric field times the area of either of these two plates times the permittivity of free space over 2. So we have the potential electric energy will be equal to the electric field times the area times permittivity of free space times over 2 times another electric field times distance, right? So we know that the voltage across these two plates is given by the electric field times the distance between these two plates. If you can still recall the voltage difference between these two plates, that's electric field times the distance between the two plates. So this one is equivalent to the voltage across these two plates. So the potential energy stored in the capacitor will be electric field times area times permittivity of free space is just the charge. So we have 1/2. This one is the charge, and ED is the voltage across the two plates. So we have 1/2 Q times V. Alright. So this is the potential energy stored in the capacitor. 1/2 times the charge of the capacitor times the voltage across the capacitor. Okay. Okay. We know that the capacitance of the capacitor is the charge of the capacitor times over the voltage across. Alright. Or the charge is capacitance times the voltage across. So we will plug in Q by CV. So we can also express the potential energy, electrical potential energy stored in the capacitor, which is UC. That will be 1/2. I will replace Q by CV. Then you have C times V times V. Right? So UC equals 1/2 C V squared. Alright? So we can also express the potential energy by 1/2 times the capacitance C times the square of the voltage across that capacitor. So capacitance again is the ratio of its charge per voltage, or voltage here is charge per capacitance. So we can also express the potential, electrical potential energy stored in the capacitor into UC is the electrical potential energy equals 1/2 Q, okay, times V. I will replace V by Q over C. That's Q times V is Q over C, so this is Q over C, right? So it's Q times Q. So the electrical potential energy stored in the capacitor can also be expressed in terms of Q squared over 2 times the capacitance. So this is how you express the potential energy stored in the capacitor, where U here is the potential, electrical potential energy in joules. That's the standard unit of energy. So it can be expressed into square of the charge of the capacitor, charge in coulomb, over 2 times the capacitance in farad, which is equivalent to coulomb per volt. And then also the potential energy can be expressed into 1/2 capacitance times the squared, V squared, or the voltage across the capacitor. So V here is the potential difference in volts. And then, the potential energy can also be expressed in terms of 1/2 times the charge of the capacitor times the voltage across that capacitor. So again, if you're going to charge the capacitor and then disconnect that to the voltage source, so we charge the capacitor, and then the amount of energy stored in the capacitor will be the amount of energy that will be converted into heat or any energy, like heat, light, or mechanical energy. So at first the electron will flow from this plate to that plate. So this plate will become positively charged and this plate will become negatively charged, and then disconnect and then connect that to the, let's say, bulb, and that energy will be used to light the bulb. So electrons will flow from negatively charged plate to the positively charged plate. So these two plates will become again neutral. So if these two plates are neutral, becomes neutral, then there's no more electrons that will flow. Okay? And then the work done will be zero. Work done to move the electrons is zero. So that's why no more potential electrical energy that can be used by this bulb. Let us try solving this problem involving energy stored in a capacitor. So find the energy stored in capacitor of capacitance 100 microfarad when it is charged to a potential difference of 20 volts. So we have here a capacitance and then voltage. So which equation we are going to use? Where capacitance is given and the voltage source or the potential difference is given. So capacitance is given and then the voltage source is given, so we can use this. So the electrical potential energy stored in the capacitor will be 1/2 the capacitance. Capacitance is 100 microfarad, or that's 100 times 10 to -6 farad times the square of the voltage. So we will use this. So 20 volts squared, that is equal to 0.02 joules. Okay, 0.02 joules of potential energy. To charge the capacitor, we need to move the electrons from one plate to the other plate, okay, by doing work. And the amount of work done to transfer electrons from one plate to the other plate is the amount of energy stored in the electrical energy stored in the capacitor. Okay. So the question is there energy stored between these two parallel plates of a capacitor, or is there energy stored in the region of electric field? Electric field is from the direction of electric field must be from positively charged plate to the negatively charged plate. So is there energy? Okay. So supposedly these two plates will be attracted to each other. Why? Because they are in opposite charges. But we need to separate these two plates so that we can charge this plate. Right? When you separate these two plates, you exerted force. Force that will separate the force that will separate these two plates is opposing to the electrostatic attraction between the two plates. Okay? So supposedly they will be attracted, but you need to exert force. So that is the direction of the force, and the force of attraction between these two plates will be opposing to the exerted force. Okay? So to build that relation, let us consider what we call the electric field energy density. What is this electric field energy density? So from the word electric field energy, so there is energy stored in the region of electric field, right? So the electric field energy density is expressed in mu, Greek letter mu. So the electric field energy density is the energy stored in the capacitor over, or the energy per volume. Okay, so that's the electric field energy. U sub C is the energy stored in the capacitor, and the volume is the volume between the two plates. Alright, and the electrical potential energy, or the energy stored in the capacitor, is expressed into 1/2 times capacitance times the square of the voltage difference across the capacitor over what's the volume. Okay, the volume. So this is the amount of space occupied between the two plates. This is one plate A and the other plate A. So what is the volume? Okay, the volume is length times width times height, since this is a rectangular prism, or area times the length. Alright, area times the width. Alright, so volume here is the area times the distance. This is the distance between two plates. So the volume is expressed in terms of area times the distance between the two plates, D. Alright. And we know that the capacitance, so a capacitor is expressed in terms of permittivity of free space times the area of this, either of these two plates, and these two plates have the same area, over the distance between the two plates, or the separation distance between two plates. And then the voltage across the capacitor two plates is expressed in terms of electric field times the separation distance between the two plates. Okay, so we're going to plug in the capacitance by permittivity of free space over times area over distance between them. So we have 1/2 capacitance is permittivity of free space times the area of the plate over distance. Okay, times voltage squared, which is electric field squared, times the separation distance squared. Alright, so all over the area A times distance. Area times the distance is the volume. Then we can cancel area. So this is d squared, right? Then we have d squared over d squared, we can cancel. Then area is, we cancel area. So what is left? Then we have 1/2 times the permittivity of free space times the square of the electric field. Right? So this is what we call the energy density, or electric field energy density. Energy between the energy stored between the two plates, or energy in the region of electric field, can be expressed by 1/2 times the permittivity of free space times the square of the electric field. So I have a problem here involving the electric field energy density. So the problem goes this way. What is the magnitude of the electric field required to store 1 joule of electric potential energy in a volume of 1 cubic meter in vacuum? And then if the field magnitude is 10 times larger than that, how much energy is stored per cubic meter? Okay, so let us first answer the first question about the magnitude of electric field. Okay, we know that the energy density, or the electric field energy density, is expressed in terms of 1/2 permittivity of free space times the square of the electric field. So we can derive the equation of the electric field. Then that is equal to 2 times to the electric field squared. Okay, that's 2 times the energy density U over permittivity of free space, or electric field, equals the square root of 2 times the energy density over the permittivity of free space. And the charge density U is the electrical potential energy per volume. I will not use capital V as representation of volume, since it may be mistaken as voltage across. VOL will be is the representation of volume. So since the energy is 1 joule per cubic meter, 1 cubic meter, or 1 meter cube, so the U, or the energy density, is 1 joule per cubic meter. So we can now solve for the electric field. Electric field is equal to the square root of 2 times the electric energy density, which is 1 joule per cubic meter, multiplied by the permittivity of free space. You can still remember the value of permittivity of free space, which is 8.85 times 10 is 10 to negative 12. It's the unit. That's Coulomb squared per Newton per meter squared. Okay. squared. So that will be equal to, the electric field will be equal to, the electric field is 4.75 times 10 to 5 Newton per coulomb. Okay, Newton per coulomb. Next, if the magnitude is 10 times larger than that, how much energy is stored per cubic meter? Since as you can see the equation, this equation, as you can see in the equation, the energy density is directly proportional to the square of the electric field. Okay? So when you increase the electric field by 10, so 10 squared will be equal to 100. So the charge density, the energy density will be 100 joule per cubic meter if you're going to increase it by 10, or you're going to increase the electric field by 10.